So in my recent asteroid mining video, I concluded that it would never make economic sense to bring minerals from asteroids back to Earth. But there is so much more to the story when it comes to the asteroid belt. Now, I got a lot of comments in that video talking about how there are infinite resources for humanity and that we need to expand there and settle those asteroids. And so I decided to take a look into it. I was really skeptical of this concept at first, but after running all the numbers, I now believe that humans will be able to conquer most of the asteroid belt within the next few hundred years. And the implications here are way bigger than just humans settling on asteroids. The ability to produce massive amounts of propellant will probably be the single greatest resource that allows humans to visit other star systems and eventually explore the rest of the galaxy. So in today's video, we're going to be talking about all the different ways that asteroids are going to be used in the future. And something I also really noticed is that most of the videos on my channel are pretty negative so far. So I'm going to have a really optimistic, but still realistic view in this video, and a lot more to come in this series. Okay, so people really like to say that there are infinite resources in the solar system, but the way that I see it, there's really just two main ones. The first is sunlight, so the closer you get to the sun, the more power you're going to have from sunlight. And the second one is chemicals, so the further you get away from the sun, the more chemicals are going to be available because they're not going to be boiled off by the heat of the sun. But this also has the downside that you'll have less sunlight and less power and less heat the further you go away from the sun. So for the asteroid belt in particular, it's 2 to 3 times further from the sun than Earth. So because of the inverse square law, you're looking at 4 to 9 times less heat and less power when you go out there and try to settle. Now, the habitable zone is the area of the solar system where liquid water can exist, assuming you have an atmosphere. But it's really not the entire area that advanced humans can settle. And so because of this, I came up with the Robo-Habitable Zone. And this is just the idea of areas where robots and advanced humans can expand and actually use the resources that are available. So the parts that are excluded are places like Venus and Mercury, where the conditions are too hot for people to survive regardless of how much power they have, or conditions like out at Pluto or at Saturn's moon Titan, where there's not enough sunlight and so it's going to be far too cold and you're not going to have enough power to keep yourself warm or really do anything useful. Now, the way that the Robo-Habitable Zone works is that this is the area where robotic colonies will be able to exponentially increase the number of solar panels that they have available. So it'll basically be like a sort of paperclip maximizer situation, except they'll just continue to expand and increase the amount of solar panels that they have. Now, you can see a situation where this actually works currently is on Earth. So we've seen the amount of solar panels that are generated or created every year increase exponentially. And this is because you get more energy out of the solar panel than you do from what you put into it from manufacturing the solar panel. So if you live in a warm place like Texas or Mexico or something like this, they have this idea of a payback period for solar panels. So the amount that you put in, it might take 7 to 10 or 20 years before you make that money back. And the cost actually basically represents the energy in electricity used to make it, plus all of the energy in human labor that it took to make it. But in the future, we're not going to need human labor to build these sort of colonies out in the asteroid belt. We're just going to be using electricity and energy through robots. So on Earth, even though it costs maybe 10 years to pay back the cost, the actual electricity that you get from this solar panel is returned within 1 to 4 years. Now, since the asteroid belt is about 2 to 3 times further, and there's also no atmosphere on asteroids, you get around 20% as much power as you do with the same solar panels. So for this reason, it's going to take longer to pay back all of that energy. But as long as you're getting more energy out of the solar panel than it takes to put in, then you can sort of have this exponentially increasing number of solar panels over a long period of time. Okay, so even if we're not increasing the rate of solar panel production, we're still going to get an increasing number of solar panels over time onto infinity because it takes longer for the solar panels to decay. Now, this actually isn't a correct assumption to make because as the power that we're generating increases, we're going to be able to increase our rate of solar panel production. So for this reason, we're going to get a sort of exponential model, and the number of solar panels in the area that we're covering is going to increase exponentially over time. So you can see here over a period of 500 years with these assumptions, you could sort of probably cover the entire surface of pretty much any asteroid. Now, as our technology advances, we'll be able to shorten the payback period, and we'll be able to make the exponential go even faster and faster over time. And what this is going to do in the long run, it's going to increase the size of the Robo-Habitable Zone. So we'll be able to expand to more of these asteroids and start building these exponentially growing robotic colonies. Okay, so some people are probably asking, what is the point of settling all these asteroids if it's not that much resources compared to Earth? Well, it actually is a significant amount of resources. For one, if you covered the entire surface of Ceres, for example, which is the biggest object in the asteroid belt, you'd produce 20 terawatts of power. So this is actually the current consumption of all energy on Earth. You also are looking about around 200 petatons of H2O, and this is actually more than all the fresh water on Earth, and you could use this to create pretty insane amounts of rocket propellant over time. Also, with that much power, you'd be able to basically host any kind of human civilization that you want on that planet. You could have whatever sort of greenhouses or structures or robots. You could pretty much do whatever you want with that level of power. And of course, humans have this concept of land ownership, so we see all this valuable land that's going to be really valuable in the future. Once we have the technology to go out there and settle it with these exponentially growing robot colonies, it's going to be a total race to see who can get there first and plant their flag and conquer this territory. Okay, so continuing on with using Ceres as an example, this would probably be one of the prime targets for starting one of these robotic colonies. So first of all, it's 2.77 astronomical units away from the sun. So if you consider that there's no atmosphere on Ceres, you're going to be looking around 20% of the flux you would get at the equator, like during noon on Earth. Okay? And now for the temperature, it's true that it is very cold at minus 143 C at the worst. But you also have to consider that there's no atmosphere. So the heat transfer is going to be much lower, and it's not going to be something that you're going to have to worry about that much. In fact, the only heat transfer that you'll really have, as long as you insulate the ground, is going to be coming from your own black body radiation going into space. So as far as the crust goes, there's actually pretty much everything that you need to make solar panels. Okay, so there's tons of water, and then there's tons of different types of rocks, which have oxygen, silicon, and iron. Now, when we look at a solar cell, you'll notice that almost all of these elements are present at the crust of Ceres, or most asteroids, really. So most of the weight is actually be in glass and just the structural components of the solar cell. And there's just going to be a little bit of metals that you could either import from Earth, or you can actually mine aluminum from the surface of Ceres. But actually, the biggest input into the solar cell in terms of energy actually comes from making the silicon wafers that go on top of the solar cell. Okay? So this is only 1 to 2% of the mass, but it ends up actually being the majority of the energy used. Okay, so as far as replicating most of the components, you're basically just going to need a furnace to make these. And so you can see this one I found on Alibaba. I could probably melt, stuff like glass or steel. Those are usually much smaller. This one's only 500 kilowatts. However, when it comes to melting silicon and refining it into that really pure silicon wafer, you need a much, much hotter furnace. Okay, it's usually up to 2,000 degrees Celsius. And you can see this one, which melts nickel, doesn't even get hot enough to melt that. And it actually is 7,000 kilowatts, so 7 megawatts of power. Okay, so in a sort of a highly idealized furnace, maybe the lightest one we could possibly take out to an asteroid, we're still going to probably assume it's going to use on the order of 5 megawatts of power or more. Okay, so to produce all this power, of course, we're going to need to use solar power. And so just starting with this random solar panel I found on Amazon, we're going to calculate how much mass that would be to produce 5 megawatts of power. Okay, so if you divide 5 megawatts by 20 watts per panel, which, again, the solar panels are going to produce around 20% of the power that they would on Earth, you end up with around 250,000 panels, okay? And so this works out to around 1,500 tons, which is pretty doable, actually, but it's a lot less than a lot of people think you need to have a self-sustaining colony. One of the things that Elon Musk always says about Mars is that he needs to have around 1 million tons of year to the surface of Mars to get a self-sustaining colony going. But you can see this isn't necessarily true when you're using robots and you have high technology and sort of the stuff that we'll have 50 years from now or further than 50 years from now. So as far as how we're going to try to get there, we can actually do this using modern technology and even using something like a modified Starship. So here are just a few things you need to do. You wouldn't be able to reuse it because, of course, you wouldn't be able to go back to Earth. and you wouldn't want to have a heat shield or sea level engines. Those would both make it significantly more efficient. And then you could refuel it in LEO with up to 15 refueling flights. And then just in case that wasn't enough delta V, even if you're using gravity assist, then you could just add a third stage onto the payload and have that do some electric thrust to get you all the way to the asteroid that you want to go to. Oh, and you would also need a very small landing stage to give you just a couple hundred meters per second of delta V just for that final landing on the asteroid, if it's one of those large asteroids like Ceres. So, assuming 20 years from now, this Starship is fully mature and all our technology is fully mature, I could sort of estimate that it's going to get there in around 5 to 10 years, like some of our probes, like the one that just went to Psyche, and then it'll probably cost less than $500 million in what we consider money today. Now, if you add up all the costs of this Starship / electric thruster mission, it's probably going to look around $830 million, and this is because you're probably going to need to do up to 15 refueling flights with Starship, so that's going to be a lot of natural gas used, and then it's also going to be a lot of development. Even if you had a big production line of these things, you can still imagine it's a lot of work to build these massive Starships that we're not going to be reusing. Okay, so of course, you're going to need a lot more than solar panels if you want to create this giant self-replicating factory on the surface of an asteroid. So like I said before, the first thing you're going to need is a giant electric arc furnace that's capable of melting and refining silicon. And so this is going to be at least 50 tons. And, it's possible you can make parts of it with stuff you find in the asteroid, but for the most part, that's going to be at least 50 tons there. And you're also going to need to bring a lot of smaller furnaces to refine other metals and glass, of course. You're going to need a lot of furnaces to refine glass. And then the second thing you're going to need is a basically giant factory or warehouse or whatever you want to call it to basically fabricate the wafers and fabricate the solar panels. So this is basically going to be a sort of medium-sized fab or big factory here on Earth. So that's looking around 500 tons. And the solar panel manufacturing process is actually not that complex compared to the actual wafer manufacturing process. Okay, and then next, I'd estimate you need at least around 100 tons of mining equipment. So this will be stuff like bulldozers to kind of gather up the sand and put it into the furnaces. Basically, tons of different types of robots, and especially like humanoid robots to just move things and control things. I also sort of estimate that you're going to need big construction equipment like a crane and all sorts of different construction equipment like that. And then also you're going to need a massive amount of robots to just operate everything. So I just said 50 tons of robots. Okay, so this works out to around 2,250 tons. And again, I'm being very generous with all these numbers. This is sort of the minimum weight that you would need to even produce any solar panels on the surface of an asteroid. Okay, and so this is going to take around 23 of these asteroid starships. And if you use my valuation that we created earlier, you're looking at around $19 billion in today's budget. Now, this is actually super doable, considering this is actually less than the budget of NASA and less than a lot of the government agencies that we have today. And it's actually low enough that, a lot of billionaires, if they wanted to go start a colony somewhere, they could go ahead and do that. And again, this is 20 or 50 years from now. Now, another thing that you would want to consider when you're first starting the colony is to massively increase the efficiency of the solar panels that you're bringing, is to mostly only bring the silicon wafers at first, okay? So these are already going to be the prefabricated silicon wafers, which is the most complex process. They're already going to have the doping process finished, which you could do on Earth with just a little bit of trace chemicals. And then all you're going to need to do is create the structural components and the wiring and just simply place those into the solar panels. You can also make a much simpler solar panel design in these factories because you're not going to have to worry about vibrations or weather or really any of the sort of extreme events that we sort of expect over the lifetime of something on Earth. Okay, so you can see here with just one extra Starship full of silicon wafers, that's only going to cost you another $800 million of transportation. Of course, those are going to be really expensive to bring 100 tons of silicon wafers, but that's basically going to enable you to create up to 20 megawatts of power instead of just having a 5 megawatts from bringing your own solar panels, okay? So the idea is you start by bringing these wafers, and then you can really rapidly expand your power generation until you can produce your own silicon wafers. And then once you get to that point, you're just going to have this exponential, crazy amount of growth in solar panels, especially if the robot technology is really good around 50 years from now. Okay, now one more thing I thought about is this concept of doubling your power by always having your solar panels facing the sun. So when you're on a large asteroid, it's going to have a night and a day, just like a planet. And so your solar panels are only going to be facing the sun for, at best, one half of the time. And most of that time, they're going to be at the wrong angle. They're not going to be pointing directly at the sun. But if you put all of your solar panels onto a spaceship, they can always be pointing directly at the sun. And if you could fabricate a spaceship that's large enough to put on all of the mining equipment and then all of the different types of fabrication and refining equipment, then you could continually increase the size of the spaceship and just keep adding on solar panels as it keeps increasing its size and it keeps mining all these smaller asteroids. And the whole entire time, all of these continually increasing solar panels are just going to be pointed directly at the sun. Okay, so as far as surviving or doing stuff on the surface of an asteroid, it's basically going to be super trivial once you have that level of power. Once you're producing gigawatts or terawatts of power, it's going to be very easy. And actually, it's pretty doable before that. So the level of light that actually gets out to asteroids is actually enough light to start photosynthesis, believe it or not. This would be the sort of plants that can survive in the shade under trees, for example. So they just need a little bit of sunlight. And then what you need to do there is just provide the water, which is pretty abundant on these asteroids, and then just keep the room or the greenhouse to a good temperature. But again, you can also have a lot of passive heating and cooling in these places, just with some good insulation around the edges, and then yeah, you could do whatever you want. You're going to have tons of power. You could pretty much do everything that we can do here on Earth. And now the final massive thing about asteroid mining is that since there's so much water, like I said before, you could do electrolysis on the water, and you could break it up into oxygen and hydrogen. And when you have oxygen and hydrogen, those are some of the most efficient rocket propellants when you use them together. And so this is going to really enable a lot of space exploration. And so I'm going to be talking about sort of this concept and some other concepts of getting to other solar systems in one of the future videos in the series. Okay, guys, so to conclude, I think our technology just needs to increase a little bit more, and this Robo-Habitable Zone will pretty much extend through the entire asteroid belt, and we'll be able to conquer it within the next 200 years, I would say. And really right now, I could see us doing it in around 20 years, and the only thing that's really holding us back is that technology of robots and their capability, and of course their intelligence. Okay, so once robots are able to run an entire fab and run an entire silicon refining operation, then I think we're pretty much good to go, and we could pretty much go get the, I'm not going to call it near infinite, but it's similar to the amount of resources that are in Earth, and it's actually even better for as far as expanding into the galaxy. So with that being said, let me know what you guys think in the comments section. Make sure to like and subscribe to the video. And and share it with your friends. And of course, have a great day.